Hello again. So in this session we'll be looking at the parameter estimation for simple linear regression. There are many methods of estimating parameters. The one we'll consider here is what's called method of least squares. So the idea here is we've got three parameters, beta naught, beta 1 and sigma squared to estimate. The first we'll be looking at beta naught and beta 1, and so we'll denote by b naught and b1 the estimates of beta naught and beta 1. And so the fitted values here what we get from the linear regression. So put the values of the parameters in there, in xi, and what we get here is what we call the fitted value of the data point at that point. The residual is the observed minus the fitted, as before, as in the other case. So here the observed is y, and the fitted is as from the regression equation. And so what we do is we take a look at trying to minimize the residual squared, the sum of the residual squared, to estimate beta naught and beta 1. In other words, we want the smallest value of Ri squared that we get by selecting the appropriate values for beta naught and beta 1. Now, there are many ways, again, of finding the values of beta naught, beta 1. Those who have done calculus could just essentially maximize, or minimize in this case, the value of Ri squared with respect to beta naught and beta 1. B naught beta 1. So the things we'll be using here is algebraic tricks, algebraic ideas. The first is we know from our earlier work on the numerical sums of data and summation notation that the yi minus c squared is a minimum when the c is actually the mean of the y's. And the second is if I've got ax squared plus bx plus c, where a is negative in this case, so it's upside down parabola, and positive, the minimum occurs when x is negative v on 2a. So something like this over here, parabola, that looks like this, ax squared plus bx plus c. The minimum value here is when x equals negative b on 2a. This results just from the parabolic relationships. And the third is, we know that a plus b squared is a squared plus 2ab plus b squared, with a minus, and the minus appears in front of the 2ab. So the Ri squared, the expression is yi minus b naught plus b1 xi whole squared. And I'm going to rearrange this. So I write the thing is putting together the yi minus b1 xi minus b naught squared. Now, so the first thing I'll use is the fact that if I've got something like this here with data yi xi minus something else squared, that is a minimum when this is equal to the average of those. So b naught is the average of y bar minus b1 x bar. That gives us b naught. I now put the value of b naught back in here. So I've got yi minus, and that expression, b naught is y bar minus b1 x bar plus b1 xi. And I'm going to regroup the terms. So the yi minus y bar, that needs to be the y bar over there. And then minus b1 xi minus x bar. And this is an uppercase x bar as well. Sorry about the typo, something went wrong there. Squared. So now I'm just going to square this in the usual way. So I get the first thing squared minus 2 times, the first thing squared, minus 2 times this times cross terms, so minus 2 beta 1 xi minus, sorry about the typos there, something went wrong there, xi minus x bar and yi minus y bar. And then finally I've got the xi minus x bar squared. Now, I'll define some of these terms because these are just data-based. The sum of squares of y is that first term. And the sum of squares of x is that last term. And the middle term is the mixed sum of squares. So now I've actually written this differently. I've got xi minus x bar times yi. So essentially the y bar here has been dropped. And you can see from the next slide why that occurs. And this is something we did do earlier in the course. So then my residual sum squared becomes b1 ssx, b1 squared ssx, minus 2b1 ssxy and plus ssy. And now this is parabolic. So this is my variable, the b1 squared and the b1, and the coefficient essentially is ssx minus 2 ssxy and plus ssy. So this thing is a minimum when the b1 is equal to negative twice this term, negative of negative 2b b1 ssxy over twice of a, which is 2 ssx. So you can see the 2's cancel off, and I get here that my estimate for b1, which I'm calling b1 hat, which I sometimes also write as b1 small case, the observed value is ssxy over ssx. The mixed sum of squares the cross sum of squares over the sum of squares of x, and beta naught, as we had before, b naught hat was y bar minus b1 x bar. So those are the parameter estimates. Now, as an exercise, I'm going to show when I do start with xi minus x bar times yi minus my y bar, the sum of, I can simply drop the y bar and get this expression here that I've got, or alternatively, I can simply drop the x bar and get the other expression. In either case, they're both equal to the last term there. Also, xi minus x bar squared is a special case of this where the y is equal to x's. So that also follows xi minus x bar times xi, and also that becomes xi squared minus nx bar squared. And finally, we can show that the same happens with the y's. Now, one thing to notice here is that because b naught is y bar minus b1 x bar, I can rewrite this as y bar equals b naught plus bx bar. So essentially, the equation of regression was y equals b naught plus b1 x. And you can see if I put x bar y bar in this equation, it's satisfied, which means the point x bar y bar always lies on the equation of regression. The line of regression goes through the average values. As an example here, for the FARMX data, I've got the summary statistics given. Sum of xi, sum of xi squared, sum of yi, sum of yi squared, and so on. So the first thing is sum of squares of y. If I use the formula, it's going to be sum of yi squared minus n y bar squared. I calculate that. Similarly, for sum of x's, it's sum of xi squared minus nx bar squared. I calculate that. And then the midsum of squares is sum of xi yi minus nx bar y bar. So I've got that as well. So I can use those to work out now. B1 is SSXY by SSX, which is 0.7623. Likewise, B naught is y bar minus B1 x bar, and that comes to 25.13. So my expression here for the fitted line of regression is the estimated sales is 25.13 plus 0.7623 times promote. So sales here is the estimate of the average sales as a percentage of that of the competitor. The intercept is 25.13. That means if I spend nothing on promotions, on average I sell 25.13% of my competitor. The slope is 0.7623, which means if I increase promotions by 1% of that of my competitors, then the sales will go by 0.7623%. And finally, just what we said earlier, interpreting the coefficients. Beta naught is the intercept. That's essentially for doing nothing. Beta 1 is the slope. So it's the average change in y. So that will be an increase by beta 1 if beta 1 is positive, and a decrease by beta 1 if beta 1 is negative. For a unit increase in x, change in x by 1, whatever the unit is, then y will change by beta 1. So here, if FARMX does nothing on promotions, it actually sells 25.13 of its competitor. Every percent increase, it sells 0.7623. So the questions here are, if FARMX wants to match their competitor's sales, what should they spend on promotions? And if they spend the same as their competitors, what are the average sales? So this will give us an idea, essentially, after working out whether FARMX actually is doing okay in comparison to its competitor. So if you do those parts of the questions, we'll understand that. And in the next lecture, we'll be looking at partitioning sums of squares to then move towards some hypothesis testing. Thank you.